Section 10.2, Checking Conditions for a Multiple Regression Model, Video 3. In the previous video, I introduced the concept of a residuals versus fit plot, and in this one, I'm actually going to construct one to show you something important. It's kind of messy over here, but what I have is this quote-unquote line of best fit, and the reason I call it that is because this was randomly made. I don't know if this is the equation. Chances are it's not, but we'll say it's y hat equals 9.5 plus 2x. That is the equation of this line. I just don't know if this is the actual equation of the line of best fit for this scatter plot. I circled the points in red to make them easier to see. And above each point I have its ordered pair. So this would be a simple regression with an x and a y, but the ideal will convey it for multiple regressions. And for each point I've also labeled it A, B, C, D, E, F, G, H, I, J, K, as I did over here. And for each point we're going to calculate two things. What is its residual, and what is the predicted value? Actually, we should calculate the predicted values first because we need those to calculate the residuals. So for each point, you'll notice that the x is either 1, 2, 3, 5, 6, 7, or 8. So all we would have to do to calculate the y hats is to plug in those x's. For example, every point where the x coordinate is 1, that would be A and B. The x is 1, so if we substitute 1 here, we should get, well, first off, this isn't the correct equation. I'm glad I caught this now. The equation of that line is 9.5 plus 0.5x. Its slope is a half, not 2. So let me try this again. Points A and B both have an x value of 1. So for A and B, the predicted value would be what we get when we substitute 1 here. 9.5 plus 0.5 is 10. So for A and B, both of their predicted values are 10. C and D both have an x of 2, and so if we substitute 2 here, we would get 9.5 plus 1, which is 10.5. Points E and F both have a value of an x value of 3, so if we substituted 3 here, we would get 9.5 plus 1.5, which is 11. So E and F both have predicted y values of 11. G and H both have x values of 5. So if we substitute 5, then we would get 9.5 plus 2.5, which is 12. Point I has an x value of 6, so if we substitute that here, we would get 9.5 plus 3, which is 12.5. So 12.5 is the predicted value for point I. Point J has an x value of 7. Substituting 7 into the regression equation, we would get 9.5 plus 3.5, which is 13. And then lastly, point K has an x value of 8. Substituting 8 would give us 9.5 plus 4, which is 13.5. So there's the fits, if you will. Now we need to, and actually I meant to make that the second column, not the third one. Oh well, it is already done. To calculate the residual for each point, we just take the observed y value minus the predicted y value. So the observed y value on point A is 17, but we predicted 10. 17 minus 10 is 7. For point B, we observed 15, but predicted 10. 15 minus 10 is 5. For point C, we observed 14, but predicted 10.5. 14 minus 10.5 is 3.5. For point D, we observed 12, but predicted 10.5. 12 minus 10.5 is 1.5. For point E, we observed 11 and we predicted 11, so the difference is 0. For point F, we observed 10, but predicted 11. 10 minus 11 is negative 1. For point G, we observed 10, but we predicted 12. 10 minus 12 is negative 2. For point H, we observed 11, but predicted 12. 11 minus 12 is negative 1. For point I, we observed 13, but we predicted 12.5. 13 minus 12.5 is 0.5. For point J, we observed 15, but we predicted 13. 15 minus 13 is 2. And for point K, we observed 18, but predicted 13.5. 18 minus 13.5 is 4.5. So those are all the residuals. The reason I regret having the columns in the order that I do is that when we plot these, we plot the predicted y value first, followed by the residual. So we need to plot the points y hat, comma, residual to make our residuals versus fits plot. So our first point is over 10, up 7. So if we go over 10 and up 7, that puts us about here. Our second point is over 10, up 5. Our third point is over 10.5, up 3.5, so about here. Our fourth point is over 10.5, up 1.5, so about here. Our fifth point is over 11, up 0, so right on the 0 line. That makes sense because point E, what we observed is what we predicted. The next one is over 11, down 1. And then over 12, down 2. And then over 12, down 1. Over 12.5, up 1/2. Over 13, up 2. And then over 13.5, up 4.5. So about here. So if we were to relabel the points, this would be A, B, C, D, E, F, G was down here, H, I, J, and K. So what happened? Well, I should have probably mentioned at the beginning that using a linear regression for this scatter plot is not a good idea. Why? It's curved. Now this was in 2 dimensions and we could see it easily, but if this were a multi-dimensional scatter plot, you couldn't see that. But what do you notice about the residuals versus fits plot? It's also curved. So what does that mean? I know it's a big step to say it worked for a simple, so it also works for a multiple. But a residuals versus fits plot will preserve curvature in a scatter plot regardless of the number of dimensions. This was just a number of dimensions we could observe, 2 dimensions and 2 dimensions. Then again, we could see the curvature here. Remember, in a multiple regression, it does not matter how many explanatory variables you have. Every data point has one predicted y value and one residual. And therefore, we can plot it in 2 dimensions and get a look at it. We'll summarize in the next video what just happened and address the other things that could go wrong, increasing variability and outliers.